continuing sequences. So limit of a sequence. Let an be any sequence and L be any real number. Then L is said to be the limit of the sequence. Limit of the sequence if for given epsilon positive however small there exist m belongs to natural number. M here depends upon epsilon such that mod an minus L is less than epsilon for all n greater than equals to m. Means first few terms of the sequence are not following this, but maximum up to infinite terms, every term following this rule, and every term is approaching towards L as n tends to infinity. Limit n tends to infinity, an is equals to L. And modifying this definition further, after opening the modulus, it becomes L minus epsilon, L plus epsilon interval, where every term of the sequence lies except few terms. Like suppose this is L plus epsilon and L minus epsilon. Most of the term lies in this region except first few terms. Like suppose A1 is not lying in the above interval, A2 is also not lying, A3 or A4 are somewhere lying in the boundary. So AM onwards, each and every term lies in the neighborhood of L. Then we say L is the limit of the sequence. Here the thing is, the first m minus 1 terms of the sequence are not lying in the interval L minus epsilon, L plus epsilon. And where the interval has a size because of the epsilon is very minor quantity, means the every term of the sequence is approaching to L, and m minus 1 terms are left out from this interval, and this interval is totally depending upon epsilon, and even the choice of m is also depending upon the epsilon. We can reduce the size by choosing the appropriate epsilon, means we can adjust epsilon, but whatever choice of epsilon be taken, if most of the terms of the sequence up to infinity lying in this interval where the L which is the interval which is the neighborhood of L, then we say L is the limit of the sequence. Now what is convergent sequence? It's directly related to limit of a sequence. Once we have found the limit, means the sequence is convergent. If limit n tends to infinity, an is approaching to L, then we say the sequence an is convergent and it converges to L. And mathematically or in the definition in the form of the real analysis, the definition of convergent is exactly same as the definition of the limit. A sequence an is said to be convergent and converges to L, converges to a specific limit we need to say, so we are saying this L. If for given choice of epsilon, however small, there exists a positive integer m such that an minus L modulus less than epsilon for all n greater than equals to m. Leaving first few terms of the sequence, all the terms other than these first few are lying in the interval of in the interval which is the neighborhood of L, means every term is approaching towards L. Now theorem based on this is every convergent sequence has a unique limit. Means a particular sequence cannot converge to more than one limit point. Or we can say a sequence cannot converge to more than one limit. So for the proof of this, on the contrary, let us assume the sequence converges to more than one limit point. If possible, let the sequence an converges to two limits which are distinct limits L and L dash. Converges to two different real numbers L and L dash. Now since L and L dash are distinct, their difference will give us some positive value, whichever is higher. So that's why we are taking mod here. The modulus of L minus L dash divided by 2 is a choice of epsilon. So this will be a positive because L and L dash are distinct. We can choose this as epsilon. Epsilon is positive. Now using the definition of convergence, since the sequence is converging to L and L dash, we can apply the definition of convergence for both limits L and L dash. The definition which we have studied above, an minus L modulus less than epsilon for all n greater than equals to m. So we'll be getting different m for different limit, right? So for the first one, for L, given epsilon positive, there exists a positive integer m1 such that an minus L less than epsilon by 2 for all n greater than equals to m1. m1 is a specific term up to which the first few terms which are not following the criteria, they are in this. And if the sequence an converges to L dash, then for given epsilon positive, there exists a positive integer m2 such that the same condition hold for L dash. Now here the positive integer is different because we will be getting different m for different limit. Now suppose first criteria is followed for n greater than equals to 5, m1 is 5 and m2 is 10. Second criteria is followed by the number which is greater than equals to 10. So we will be taking the maximum of 2 so that both the condition holds at one specific m. So let m be the maximum of m1, m2. So if one is following at 5 and second is following at 10, so we will be considering at 10 first and 2, both the condition will hold good. So now L minus L dash modulus, taking minus a and plus a and in between, following the triangle inequality, we'll be getting this separated L minus an and an minus L dash. Again we can reverse L minus an as and en minus L because in modulus it doesn't matter. And since both the condition holds for n greater than equals to m, so epsilon by 2 plus epsilon by 2 collectively is epsilon. That's why we have chosen this as epsilon by 2, so that in the end we can get this as epsilon. And choice of epsilon is totally on us, so you can choose different possibilities with epsilon. L minus L dash modulus is less than epsilon, which is a contradiction as we have assumed epsilon as half of this quantity modulus L minus L dash. So this is contradiction to our own assumption. So this implies our supposition was wrong. If we choose two different limits, we arrive at contradiction. Hence, two limits are not feasible. There is a possibility for only a unique limit for convergent sequence. Sequence converges to a unique limit.